In infinite-dimensional mathematics, finding exact solutions to massive datasets or complex continuous functions is often computationally impossible. The search space is too vast. Yet, even when an exact solution does not exist, the underlying geometry of these spaces guarantees the existence of a single, rigorously defined best approximation. The formal proof of this guarantee is detailed in Chapter 6.5 of Erwin Kreyszig's Introductory Functional Analysis with Applications. The challenge is calculating this exact closest vector in an abstract space where physical distance cannot be measured with a ruler. To solve this, we operate within an inner product space, a vector space equipped with an algebraic operation that allows us to define angles and lengths geometrically. When an inner product space is mathematically complete, meaning it contains all of its limit points and has no structural gaps, it is defined as a Hilbert space. This notation shows how the inner product induces a norm. Taking the square root establishes a rigorous definition of distance. Within this Hilbert space, we isolate a specific subset of vectors, forming a closed subspace denoted as y. Completeness and closed subspaces are absolute prerequisites. They ensure that as we calculate closer approximations, our target vector actually exists within the designated space and doesn't vanish into an undefined limit. This diagram visualizes our objective. We have a target vector x floating outside a closed subspace y. We need to approximate x using only the vectors available on this plane. This equation formally defines the best approximation. We are looking for a distance, delta, which is the infimum, the absolute greatest lower bound, of the distance between x and any vector y within the subspace. If we test arbitrary vectors across the plane, the resulting distance to x continuously shifts. The minimum possible distance is achieved exclusively when the connecting line drops at a 90-degree angle to the plane. This geometric truth is formalized by Theorem 3.34, known as the projection theorem. The theorem allows us to decompose our original vector into a simple addition, x equals y plus z. Here y is the orthogonal projection of x onto the subspace, and z represents the orthogonal error vector, the precise difference between our approximation and the exact value. Because distance in a Hilbert space is strictly defined by the inner product, orthogonality dictates the absolute shortest path. Translating this geometric intuition into a numerical solution requires shifting from abstract theory to coordinate-based calculation. This chalkboard shows our approximation, y, expressed as a linear combination. We assume the subspace is finite-dimensional, meaning it is spanned by a specific basis of known vectors, y1 through yn. To construct y, we need to calculate the exact scalar coefficients, alpha k, for each of these basis vectors. We apply our geometric constraint. The error vector, x minus y, must be completely orthogonal to every basis vector spanning the subspace. Stated mathematically, the inner product of the error vector and any basis vector yj equals 0. We substitute our linear combination into this inner product in place of y. Because the inner product is a linear operation, we expand the expression and factor the coefficients out of the calculation. Rearranging the terms yields a final system, known as the normal equations. We have successfully translated the abstract concept of an orthogonal projection in an infinite-dimensional space into a finite n by n system of linear equations that can be computed directly. This system provides the coefficients, but under what specific mathematical condition is this system guaranteed to have a unique solution? This matrix visualization introduces the Graham determinant. Denoted as G, it organizes all the inner products of our basis factors into a single structural grid. Theorem 6.5-1 states that our basis elements are linearly independent if and only if the Graham determinant does not equal 0. If the vectors are linearly dependent, one of the vectors is merely a linear combination of the others. In the matrix, this renders an entire column redundant, forcing the determinant to 0. Conversely, if the vectors are strictly linearly independent, the determinant is non-zero. This proves the coefficient matrix is invertible, and our solution for the approximation is unique. This equation expresses the exact distance from our target vector x to the subspace, using solely Graham determinants. It is the ratio of the determinant of the target vector alongside the basis, divided by the determinant of the basis alone. The geometric requirement of minimum distance is expressed entirely through the relationships within this matrix of inner products. We can map this Hilbert space logic directly onto specific practical function spaces, such as L squared AB, the space of square integrable functions. This split-screen visualization demonstrates how the framework applies to actual data. On the left side, by choosing polynomials as our basis vectors, the exact same orthogonal projection we just derived maps a noisy scatterplot onto a smooth curve. This establishes the rigorous mathematical foundation of least squares approximation. If instead we select trigonometric functions as our basis, the orthogonal projection takes a complex, jagged signal and decomposes it cleanly into smooth sine and cosine waves. This application drives Fourier series analysis, the mechanism behind all modern signal processing. Furthermore, these derivations govern how we extract observables in quantum mechanics and categorize data using kernel methods in machine learning. These fields rely on the same geometric engine, orthogonal projection, to solve their respective optimization problems. We began with the challenge of pinning down a precise value in a space too fast to measure physically. By demanding mathematical completeness, the geometry of Hilbert spaces guarantees that an exact, unique best approximation always exists as an orthogonal shadow. The Gram determinant provides the explicit computational mechanism to locate it, translating infinite dimensional abstractions into solvable linear algebra. These derivations provide the framework for investigating the internal properties of linear operators. We can now move towards spectral theory.